Hello, this is MAT221. This is Mrs. Johnson. This is Calculus 1. We're in section 5.1 on areas and area underneath the curve. We were talking about rectangular approximation methods, and here we're talking about given the data of an object, of the velocity of an object, we can use the data to find the approximate distance that the object has traveled, or the accumulated amount of change in the distance over this interval, by using the RAM methods. Now, we looked at this one, which all I did was take the data and graph the data, and then I drew the LRAM, where the left corner of each rectangle is hitting the curve. Now, I could add these up easily. It would be, this value would be 25 times 5, then 31 times 5, then 35 times 5, and so forth. And if we do this, if you notice, I'm using, for an LRAM, I was using the first value, the second value, the third value, every one except for the last value, because if you notice, I'm not using the value of the curve, this 41 value. I'm not drawing a rectangle that has a length of 41, but I did draw 1, 2, 3, 4, 5, 6 rectangles, 1, 2, 3, 4, 5, 6 rectangles, where their heights were given, their lengths were given by 25, 31, 35, 43, 47, and 46. So sometimes we don't even have to draw the curve to know. We can use an LRAM by just taking all of our output values and then multiply by, if you notice, by the width of each rectangle, which in this case you can see the width of each rectangle is 5 units. Adding them up, I get 1135, or 1,135 feet. Now, by the way, I didn't do it here, but I definitely could have done an RRAM here and done 41 plus 46 plus 47 plus 43 plus 35 plus 31 and then multiplied by 5. And that would have been another estimate. And then averaging the two would have been probably the best and most accurate value for how far this object has traveled. Here's another example. It says the velocity v of t in the table below is decreasing on the interval from 2 to 12, using 5 subdivisions or 5 rectangles to approximate the total distance. Find an upper estimate and a lower estimate. So what I did here was, like, I noticed that I'm going up by every 2 units here, and I wanted 5 rectangles. So I said, well, okay, 12 minus 2 divided by 5 rectangles, perfect. I have to measure every 2 units of time. The LRAM would be that width, which would be 2, and then I'm going to take v at 2, which is 44, 42, 41, 40, and 37, and add those together, and then multiply by the width of each rectangle. So all I did here was actually take the GCF of the width of each rectangle out, but I'm doing the same thing. 2 times 44, 2 times 42, 2 times 41, 2 times 40, and 2 times 37. And I get 408 as my unit. Now I don't have units as far as feet or anything here, but I'm assuming it would be feet. Now I could do the same thing with the RRAM. Again, I would be 42, right? We would do 35 plus 37 plus 40 plus 41 plus 42. When we take the RRAM, we take every output value except for the first one when we draw our rectangles. Because of the way we draw our rectangles, I got 390. And of course, a good estimate would be the average of the two. Last example here, a particle moves along the y-axis with a velocity of 30 centimeters per second for 5 seconds, and then a velocity of -10 centimeters per second for the next 5 seconds. Positive velocity indicates motion is upward, negative velocity represents downward motion. What does this sum represent? Well, if we look, this sum, if we did 30 centimeters per second for 5 seconds, that would be this area. That would be my upward motion, or 150 centimeters of upward motion in those 5 seconds. And then we have here -10. So this would be the area would be my downward motion. This will always be true as we move forward, by the way. When the area lies above the x-axis, the accumulated amount of change goes in the positive direction or increases. And when we have a negative area below the x-axis, then we said our accumulated amount of change will decrease or be less or be negative. So the area of the rectangle above the t-axis represents upward distance, and the area below the t-axis represents the downward distance that was traveled. Lastly, not all rams are LRAMs, RRAMs, or MRAMs. Sometimes we do what's called inscribed rectangles, where the rectangles are all just below the curve. Notice it's a mixture. This one is an LRAM, this one is an LRAM, this one actually touches both corners, and this one is an R. So notice it's not really an LRAM, RRAM, or MRAM. It's just saying that the rectangles are all inscribed or below the curve. Here I could have circumscribed rectangles where they're all just above the curve. All right, that does it for this PowerPoint for section 5.1. You need to work on the WebAssign for section 5.1, and also there are several worksheets for section 5.1 in the worksheet folder that you can work on, and answers are also given. Have a great day.